Good morning. My name is Kayona, and I am a CSPC Evaluations and Reports Committee member. We acknowledge that the Canadian Science Policy Conference is taking place on the unceded, unsurrendered territory of the Anishinaabe Algonquin Nation, whose presence here reaches back to time immemorial. We respect our traditional hosts and thank them for allowing us to operate on this land. We are about to participate in an interactive panel entitled, just one second. Next Frontier for Quantum Applications in the Natural Resources Sector, organized by Natural Resources Canada. Please don't forget to tweet about your favorite events and panels at the conference using @SciencePolicy and hashtag CSPC 2022. Finally, please don't forget to fill out the evaluation survey for this session in the program app. Your feedback is very important to us, and we wish to continue to make CSPC even better next year. Thank you very much. Enjoy.
Thank you so much. Great. So welcome to today's session. Today we're going to be talking about the new frontier in quantum science, and it's really exciting to be here and to have such distinguished members as part of our panel. Before we begin, I would like to acknowledge that we're participating in this panel discussion on the traditional unceded territories of the Algonquin and Anishinaabe people, and we're very grateful to have the opportunity to honor their long history and to be able to have this very important discussion on their territory. And I encourage you to reflect on what that means to you individually. So I'm Brenda Dogbay, and I am Director of Strategic Policy at the Office of the Chief Scientist within Natural Resources Canada. And NRCan, which is our acronym, is a science-based federal department that's committed to improving the life of Canadians by ensuring the country's abundant natural resources are developed sustainably, competitively, and inclusively. And as a department, we are an established leader in the field of energy sources and distribution of energy efficiency, forestry, minerals, and mining, earth sciences, and data. So as you know, Canada is huge on natural resources. And with these diversified fields of operation, NRCan anticipates significant opportunities and threats of the quantum science and technologies relevant to its mandate and into the areas of its activity. The Office of the Chief Scientist has been the lead for NRCan in terms of quantum-related activities in collaboration with other departments such as ISED, Global Affairs, NRC, and it's quite exciting to have a few of those members here in the panel. The natural resource sector is one of the key sectors with the greatest near-term benefits from quantum technology applications. And quantum use cases are really important in demonstrating the exciting applications for natural resource sectors that could achieve goals for net zero emissions, energy transitions, climate action, security for critical infrastructures by supporting innovations in clean tech, in EV battery and hydrogen productions. And so there's quite a whole host of opportunities. And as you heard just from the plenary session with Deputy Minister Simon Kennedy, again, there's a lot of need for scaling up, whether it's battery use, whether it's the electric grid. And so this also presents an opportunity. Today, we'll be hearing from a range of experts from industry, from academia, from government on opportunities and challenges of quantum technologies, as well as potential for quantum to significantly support NRCan's priorities and Canada's priorities. So here's what to expect from the session today. I'll provide an introduction of each of our distinguished panelists, and they'll have about 5 or so minutes to give a high level on their perspective on how they intersect with quantum. And then we'll have a guided discussion for the rest of the panel, but we'd also like to give you some time to ask questions. So as our first panelist, it is my pleasure to present Dr. Amy Gunther. Amy is the Deputy Director of the Internet of Things, Quantum Sensors Challenge Program at the Natural Research Council of Canada, or NRC. And at NRC, she also engages across research centers and collaborative challenge programs to shape and lead the quantum communications and quantum photonics themes within the high thought put and Secure Networks Challenge Program and the QSP, respectively. Previously, Amy was the Scientific Director for Quantum and at Defense Research and Development Canada, so that's DRDC, where she co-authored the DND/CAF Quantum S&T Strategy. Amy has a PhD in Quantum Information, in Experimental Quantum Optics from the Institute of Quantum Computing at the University of Waterloo, and very happy to have you here, so over to you.
Good morning still. My slides. All right. So as Brenda has announced there, that's me. Next. There we go. All right, let's hit the next slide. That was boring. All right, so what are these? What she mentioned, I'm part of a challenge program there. So this was a push that came out of Budget 2017, the Innovation and Skills Plan there, there was a push for a lot of different innovation programs throughout government there. And the National Research Council of Canada, so we have a lot of research centers and researchers within government. So how does that stoke some innovation? Hit the next slide. So what this particular program is a collection, is a portfolio of projects that an internal researcher from our different research centers, so we have a lot of, say, quantum photonics and whatnot, with external researchers from, say, academia, from industry, some of the startups, small, medium enterprises, and together they make up what we call a challenge program there. So this is a grants and contributions program there, so we fund to enable this collaborative research and development. And why is this relevant here? This is something that, in addition to going after the Innovation Skills Plan, is also was part of the National Quantum Strategy, which is to be announced, as we're still waiting for there, as well as one of the focus areas of the D&D-CAF Quantum S&T Strategy in quantum sensing. So, of the policy relevance, this is kind of where we're at. What is quantum sensing? Let's get to the bury the lead there. So we have projects across Canada, also international projects that sense all types of things. Lots in the optics and photonics, so say with visible light, infrared, measuring, say, current or magnetic fields, all temperature, all sorts of things across Canada, as well as, since this is mostly academic, is predominant of our stuff, this is averaging a technology readiness level 2 to start with on average to about 4.5. So that is a skewed distribution that gets out to. We have some higher ending TRL projects, maybe about 8 or 9. But on average, that's what you expect in some of the university areas right now. But we engage a lot within the federal funding ecosystem as well, with a lot of our other innovation peers, such as Ideas and Innovative Solutions Canada. What we envision as ways that we can help continue to accelerate quantum into the forward direction to offload these innovations to actually get to some of these other application areas at the end of the day. It's a bit too soon right now. These 7-year programs, we're just in year 2, just a little getting going here. But for my neck of the woods in the quantum sensing space, we have a lot of action going on here with the doubling of our program size, thanks to the National Quantum Strategy. We still have much more appetite across Canada of excellent world-class quantum sensing-esque research to be done. So this is plenty of a big open space right now in some exciting times.
Thank you so much. Next, I'd like to welcome Professor Shohini Ghosh. Shohini is a professor of physics and computer science at Wilfrid Laurier University and holds the NSERC Chair for Women in Science and Engineering in Ontario. And her research focuses on quantum information theory and quantum chaos. Shohini advocates for women scientists as the founding director of the Laurier Center for Women in Science, and as the first Canadian member of the International Union of Pure and Applied Physics working group on women in physics. She serves on the scientific board of the UNESCO International Basic Science Program and was past president of the Canadian Association of Physicists. Really privileged to have you here. So over on to you.
Thank you so much. Is this working? Yes. Okay. So I wanted to give you a bit of a researcher's perspective on the field right now. It's huge, so this doesn't cover everything. It's not comprehensive. So I just wanted to show you a couple of images and thoughts. So next slide, please. This is the most important one. You might recognize this from Star Trek. Mostly I wanted to put this up because, I always want to put up Star Trek stuff. But you'll recognize this is teleportation, sci-fi stuff. This is not what we do in quantum at all. So the reason I want to put this up is to say that we're currently in the middle of a bit of hype as well on the quantum side. So I wanted to clarify that, we do have to have a discussion that is more realistic. And we do have, by the way, quantum teleportation. That is a thing. It's not this thing. So the next slide is a bit more representative of what quantum teleportation would actually look like. This is not an actual photo, but it is a rendering of an actual satellite that was launched from China a few years ago. That was based on, that's focused on trying to develop quantum communication technologies, including things like quantum teleportation, where we're talking about teleporting quantum information, not people, and certainly not Captain Kirk. So that's something that is actually on its way to being developed and more realistic. And perhaps these kinds of initiatives in other countries should be part of our conversation, because we have to think how we are positioned compared to other countries, and how can we keep up, as well as, of course, partner and move forward as a global community in quantum. Because this is not going to be about, here's what we do in Canada, and that's what they do there. That's not going to be how quantum develops, and no matter how much we want it or don't want it. So the reality is this is something that is a global kind of technology, and it requires global cooperation moving forward. There's many potential areas. I'm not going to go into details on this slide. I've just put up a few areas where there's potential applications, but I think our conversation is going to go into that in much more detail. So I'm not going to talk about that much. I'll just say that there's, of course, a lot of government funding, not just in Canada, but around the world. And there's also a lot of private sector activity. So for example, next slide, please. This is IonQ's leadership, which is the first quantum computing company that is now traded on the New York Stock Exchange, which, seems like a big move. But you might also recognize something else about this slide, about the people on the slide. There's not really much representation of diversity at all. Sadly, this is not only the case for IonQ, and I'm sorry, I'm not trying to pick on IonQ. In fact, when I looked very recently, they do have at least one more woman on the board, so yay. That's just a first step. I don't want to end on a downer and try to criticize anybody, but this is an important conversation going forward, because we're talking about impact in so many areas of society that we can't be thinking about, building the technology without seeing who's at the table. So I want to end with a much nicer, more fun slide, which is one of my favorite slides. The reason I love this slide is everybody, all the women in this slide, they're all physicists from around the world, from over 50 countries. So this was a photo, next slide please, that was taken at the conference, International Conference on Women in Physics, which brings together women physicists from around the world. And I think this is where the potential lies for building a new kind of technology, a quantum revolution, but also a social revolution, which is really the revolution I want to see. Thank you.
Thank you so much. And we were very intentional in terms of putting our panel together to make sure that it is indeed representative, not just of the expertise, but also the diversity of thought in this area. So next, I'm going to welcome Mr. Bruno Couillard. In addition to leading the Crypto for A team, Bruno also leads its technology division and product architecture, and he brings more than 30 years of experience in the fields of technology and cybersecurity, both in the public and private sector, including the Canadian Armed Forces. As a board member of Quantum Industry Canada Association, co-chair of the Quantum Industry Developers and Users Working Group, of which we're both members, as well as Bruno is actively involved in the promotion and development of the National Quantum Strategy for Canada, which a lot of us are involved in as well. So thank you, Bruno, for being here, and I turn it over to you.
Thank you, Brenda. Thank you for this conference and the invitation. I'm here, but I have a slightly different approach to quantum technology. Typically, what I do is I look at advances in technology, thinking about what bad things could happen and how can we protect it. So I tend to be one of those guys on panels that talks about the negative side of things. And from that perspective, those of us that have this tendency to think in terms of what could others do with quantum, there's always a notion of looking back in history, thinking about advances that humanity has made. Think of nuclear power was one that kind of caused the world a shock. And with typical big advances, usually we tend to use those new tools, those new technology, not for necessarily the best of positive outcomes. We tend to use them sometimes with negative concepts. So our view or my kind of looking at the world and the scene and the advances is always to think in terms of, can we make sure what we're building as a society, what we've now done for the last 30 years of advances on the internet, the reason why we have all of these really cool cars and smart cities and gadgets all around us that make our lives a lot faster and a lot easier. How can we make sure we protect that? How can we ensure that the future is not going to, something like a quantum computer won't destroy what we've got going? So that's typically how we're taking, or our approach. And we're also looking very carefully and following the signs of what's going on. And the reality is, you kind of have to guess, when will quantum computers arrive? When will it be possible to use those massively capable machines to break security, to break what we have today? And we have to make guess. Chances are you're not going to find out in the press release, someone has broken RSA or the cryptographic algorithms that we use today. So we have to make guesses, and we have to also look back again at historical events where, for example, when we found how to break crypto like Enigma back in the 40s, that concept was kept classified and secret for almost 30 years because it was useful. So sometimes you may not know someone is breaking your crypto or is in your systems. And I'm on that side of the house, always thinking that way. I'm sorry, it's a bit of maybe a cold idea to look to this panel, but the good news is there's a massive effort going. A lot of governments and a lot of really smart people are working hard to ensuring that all of our cryptographic systems, our security systems, our internet, everything we do that we take for granted, many people are thinking about the problem. They're thinking about ensuring that these systems will continue to be there in the next 20, 30, 40 years with all of these questions that we have up in the air. So that's my kind of look at things, and looking forward to the Q&A side of things.
Thank you. And that's kind of why we sandwiched you in the middle. So we get some good news and some not so good news. Before I invite Professor Sanders to speak, we've got seats up front. So we have about an hour more to go. So folks, if you want to settle in, there's tons of seating space up here. And while you do that, I'll introduce our next panelist. So Professor Barry Sanders is the director of the University of Calgary's Institute for Quantum Science and Technology and scientific director of Calgary's Quantum City. His research spans quantum science and technology, including quantum sensing, quantum computing, quantum communication. And Barry holds a distinguished visiting positions at the University of Science and Technology of China and at the Raman Research Institute in India. And he is a scientist and mentor with the Creative Destruction Lab branches at the University of Toronto and Calgary, and an affiliate member of the Perimeter Institute for Theoretical Physics in Waterloo. He is a fellow of the Royal Society of Canada, of the United Kingdom Institute of Physics, of the American Physical Society, and of Optica. And he received the City of Calgary's International Achievement Award in 2022. So please welcome me. Please join me in welcoming Barry to the panel today. Over to you.
Thank you. Sound is working, I guess. Okay, great. Yeah, thanks for the introduction. And so it's a great pleasure to be here. I want to take the time just to spell out where I think quantum is going and what the challenges are and the opportunities. First of all, we can break quantum technologies down into three areas. We've heard a bit about it. There's quantum sensing, quantum communication, and quantum computing. The quantum communication we can break down into network stuff, creating something known as entangled as quantum resources and distributing, or related to the securitization of networks. This is in the area of quantum cryptography. And then there's quantum computing, and then I think we'll hear about hardware from you. And so we've got quantum computing can break down into hardware development. Shohini showed the IonQ example becoming a company. There's a software side, there's algorithm development. In my mind, algorithms and software are not the same, and so it's important to understand each of the areas and where they're going. And so we have the quantum sensing, quantum communication, quantum cryptography areas. Canada has formidable strengths in all of them. The challenges that we face, first of all, this is a very deep tech area. So most of the technology that we're developing is still early stage. And so we have challenges with other fields as well that are very early stage. Shohini mentioned the hype. Hype is a problem in an early stage area because people want to find ways to promote it, sometimes paint out unrealistic expectations. I'm hoping during this session we can get better clarity on what's realistic, what isn't, what's near future, and what's far future. Amy's mention of that quantum sensing program is a good example where National Research Council is enabling translation of what's going to work into practical, and separating them. And so this knowledge translation and estimating timescales for exploiting technology is very important. Another aspect of the field is the problems are very hard. Sometimes said that no one understands quantum physics, and I'm in quantum physics, and I believe that statement. So I think none of us totally understand. On a philosophical level, there's something known as the measurement paradox. And so the idea of quantum mechanics, in order to learn things, we have to measure, and then we measure something, we see what we got, and then assimilate that into our knowledge. But quantum mechanics tells us that the notion of measurement is not possible. Like there's no objective reality that emerges. And I don't want to go into all the philosophy, but I want to say that, the field is hard, not just mathematically, not just in terms of physics and chemistry and so on, but also it's hard even on a philosophical level. But we can't let that stand in our way. We have to really solve problems and develop technology, even if philosophically we're puzzled by it. And the hardness of it means that we need really good talent. And so, of course, in Canada, there's always a brain drain problem. So we have to find ways to make sure that we keep the talent, but also it needs to be collaborative. And you heard from Brenda about the introduction. I myself have international positions. I strongly believe in international collaboration. That's getting very difficult now. So you heard one of my appointments is at the University of Science and Technology of China. So when Shohini had that quantum satellite, that's the group I'm in. So I'm also part of the group in China that's, one of the leaders in the world. And so I have this awkward position where I'm both working here and I have to manage all these different issues. How can I continue to work in China and India and still make sure that, I'm a trusted person here in this country? So it's getting more and more difficult to carry on international collaborations. And ultimately, it comes down to what, we want to use science for good and not for evil, and how to separate the two is very difficult. Recently, I've been very involved with an organization called GESDA, which is the Geneva Science and Diplomacy Anticipator. It was established by the Swiss Foreign Ministry. The Swiss Foreign Minister is now the president of Switzerland. He came to a meeting a few weeks ago that we had in Geneva. And in that respect, we're working there. The Swiss government's leading the effort, and the idea is to collaborate with the United Nations, which is, a lot of the activities are in the same city. And we're looking for ways to figure out how we can unroll quantum technologies in a way that it addresses problems of the global south. It's got the diversity issues, all these things. So we want to make sure that quantum technology is available to the planet, at the same time recognize the importance of security to prevent technology that's sensitive from leaking out. So I take that whole thing very seriously. We're working on it. And the other issue I just want to mention, is the final one, and then I'll pass it on, is what I think of as a boundary value problem. It's that quantum is everywhere, so everything is quantum. And so when we're developing quantum technology, the problem is not really what's in, but what's out. And so we haven't sorted this out. As we create resources, opportunities to do things, as we distribute resources to be able to develop things, we don't really have a clear idea or consensus ourselves in what makes something quantum and what makes something not quantum. And that's very important, because as we allocate resources for strategic areas, we have to use the resources well, and that's a policy issue. Thanks.
Thank you so much, Barry. And a lot of what you raised is what we're grappling with within government. So even getting our senior management's attention on quantum, it's so abstract. So to convince your assistant deputy minister or even the DM that quantum is important and it's worth paying attention to, it seems removed from the work that we do. But that being said, I think it's an area where we can't not act. And especially when it comes to the security implications, national security implications, it's an area that that we have to at least be engaged in and even try to be at the forefront of. So last but not least is Mr. Rafal Janik. I just need to click the clicker. Rafal is the Chief Operating Officer at Xanadu, and he manages business operations and leads organizational growth on a product and company level. And he specializes in commercializing deep tech projects and has over 10 years of experience in leading software and machine learning teams, both in large enterprises and in high growth startups. And Rafal holds an MSc in biophysics from the University of Guelph. So please join me in welcoming Rafal. So over to you, Rafal.
Thank you very much. I was originally promised some controversy. I think you'll get pretty solid agreement for most of the panelists here. Definitely being on more of the, I would say, corporate side, more of the hype side of quantum computing, we definitely face the same problems in trying to bring back some perspective to specifically what quantum computing can and can't do. Often when I talk about quantum computing, I start with like the cliche notion that Moore's law is ending, computational power growth is ending, and quantum computing is that solution. It's partially true. You can demonstrate that quantum computers, even today, can perform certain tasks much faster than supercomputers, no matter what size they are, but those tasks are fundamentally useless. So even the announcement, recently we heard from IBM having a 433 qubit quantum computer, which is probably now one of the largest that's publicly available. This is still not a device that you can use to solve real world problems. To solve the type of problems that most people in this room would actually be interested in tackling, you're talking about devices that will have millions of qubits. And there's really big technological challenges to scaling to that level of a quantum computer, but there's also really big manufacturing and supply chain issues. The number of chips, the number of semiconductor devices with processes that may or may not exist today that are required to build that device, nobody can really manufacture at that scale. and definitely not Canada independently on their own. So there's big challenges to move forward the not just technical development side, but also the fundamental supply chains in order to support quantum computing as an industry. I'll also say that the comments on software and algorithms are very valid as well. And on the algorithmic side, I'd really like to highlight that even if we had that quantum computer today, that large-scale system, there's still a really big challenge understanding where we can use it. It's not that you can take any problem you're running today and apply it directly onto a quantum computer. You actually have to rethink and reformulate that problem at a fundamental level. And effectively, we know about 3 different approaches today to tackling problems on quantum computers, and that really needs to expand to a much larger amount of algorithms. Similarly with software, where digital computing was, I would say, in the 1800s. We're not even thinking about programming with higher level abstractions. We're talking about actual circuits that we're running on quantum computers, and there's a lot of development, a lot of effort that has to be put in to solving the software side. I'd also like to add that Canada's done a phenomenal job in investing in quantum technologies really early, especially on the academic level. Since the early 90s, I would argue that Canada was one of the leaders in pushing quantum forward. We have great institutions across the country that have been able to develop as a result of that. But we are sitting now at this very bizarre crossroad where the true commercialization of quantum is still quite a ways away, and especially when you think about the number of resources that need to be invested. But we're at risk of losing the ability to commercialize that technology here within Canada because of what our partners and peers around the world are doing. So I'm really interested in learning from everybody in this room just how much value and willingness they see towards quantum computing in order to drive that commercialization of quantum locally within Canada and building up those supply chains here.
Thank you. And I think you touched on quite a number of issues around how do we create a landscape or an ecosystem where we as Canadians can keep that lead, because we've had the lead, but there are a lot of actors and a lot of players who are accelerating their investments, they're accelerating their involvements in quantum in a way that could very easily topple us from our leading role. I want to shift and perhaps ask each of you, how can quantum support priorities of our time around clean tech and energy, net zero, climate action, improving EDI? So it's a very broad question, but I think your reflections on the role that quantum could play in a very practical way. I think for a lot of people, quantum is still very, very abstract. I'm not a subject matter expert in this area. My background is in public health, but there's I think all of us are drawn to these advanced technologies and the potential that they could to solve some of our problems of the day. However, how can we make that sound a little bit more practical and tangible for our audience?
When I was poking around on this last week a little bit there, particularly angling on, say, quantum sensing for the natural resources sector, it surprised me how much gravity sensing is actually a huge player in this area. So right now, literally, if you want to make a quantum sensor to sense gravity, it's literally as cool as putting a bunch of atoms in a vacuum chamber and dropping them and seeing which atoms get pulled by the mass nearest them. Obviously, it's a little more complicated than that, but that's the general vibe of it. And some of those are already in place right now, like sitting on a volcano, watching the time over time, seeing how the mass underneath the ground there, all the magma is actually moving around. And in Canada, what does that look like? Our glaciers, through the long time over time, to see how that is changing, these real stable things. So the nice thing about atoms, the common joke, they make everything up. They also are all identical to each other. All the carbon atoms are carbon. So if you're making some of these things can have really great standards if you look at that from that side there. So there's definitely in the gravimetry side of life, I think in sensing, there's some cool stuff coming there. Canada does have some academic talent in this area, and I think more is coming every day on the position navigation and timing. atomic clocks. Of course, we at the National Research Council, we have a real fancy one there. It helps contribute to the world standard. But like, what about portable ones that actually can be brought around, and different things you could be doing using highly precise time? Magnetometry, what's underneath the ground? Are there ways we can see, either is it minerals underneath there, or like be able to use magnetic fields? Diamonds are one common way of defected diamonds are one strategy for that. Or in the oil and gas industry, using, say, atomic frequency cones, so special rulers of light that have have spikes every very defined frequency areas. You see, is methane or whatever being emitted? Can you use kind of a long distance detection to see if gas emissions? So in the sensing field, some of this stuff is moving in the forward direction. This sensing, I think, as was mentioned, is one of the first quantum technologies that is actually going to be in the adoptable stage. As was rightly pointed out, there's a long road of deep tech ahead of us, but there can be Canada has some interesting opportunities at its feet, and hopefully we can interact with, as many has already mentioned, the other powerhouses in quantum around the world, to be able to collaborate to get some of these sensors, to be able to adopt them into our different areas.
Oh. Thanks, Amy. That was a great summary. I guess I can add a bit to it. A couple of points I want to make. As Barry mentioned, there's basically these three different areas, right? There's communications, computing, and sensing. So you heard a bit on the sensing side from Amy. On the communication side, the key sort of application, no matter what specific area we're talking about, is the fact that we can enhance, hopefully, encryption of data and therefore data security. And that obviously would apply to any of these areas we're talking about in terms of making sure our data is secure. We know that one of the things that is an issue is whether or not our energy systems are safe. Are they protected from hackers and from any other kinds of vulnerabilities? So on the communications broad area, data encryption and security would be a big gain if a quantum infrastructure could be built. And that's a big challenge, of course, to try to add to our existing infrastructure. And it could take more than a decade or so. So with that in mind, it's important to start now rather than later, if we're really serious about assuming that no matter whether we know or not whether quantum computing, large-scale quantum computing will ever exist, whether it'll hack into all of our current sorts of securities, just the fact that it's possible already makes it less reliable, because a lot of safety and security is based on trust. So as you already heard, we don't quite know. When somebody does manage to get to the point where they're hacking us, maybe we wouldn't even know at the time, because why would they broadcast that, right? So those are the kinds of questions that on the data security side we have to be thinking about and would need to apply now to all of our existing infrastructure. And the other piece I want to mention, I think you'll hear from others about the computing applications, but I want to go back and say, I was watching late at night the other night the launch of Artemis 1, right? This rocket. And I'm thinking, how inspiring is that going to be? How many kids are going to dream about, studying the right sciences so they can go and be part of the next moon program, right? I think that quantum has a similar possibility where there's so much excitement. Sometimes hype is a good thing because it inspires people. So that could lead to being able to draw in young people, the next generation of scientists and researchers. And that will actually, of course, help Canada become a leader. If we can bring more young people into these kinds of fields. You don't actually have to have a physics degree to contribute to this industry. So I think that's an important piece, that as we go forward and think about how Canada positions itself, we could build the kind of workforce that could be, the envy of everybody. That would be great.
Thanks. On the, I guess the microphone is musical chair. On that front, one of the, certainly when I was thinking about the panel and what might be an interesting point or something, a takeaway, was from a policy point of view. And where I'm going to take you guys from my perspective is we're all, and the hype is all around us, the notion of whether it's quantum technology or IoT or things that are going to make our cars and homes and cities and grids smart. Everything is moving in that direction. There's a lot of things being automated. We're trying to connect everything. We're trying to make the world around us a lot better and more automated and easier to manage. What that typically does is it now opens, from a cybersecurity point of view, it expands what we call the surface of attack. So we go from a few billion machines on the internet to multiple tens of billions of machines in the next few years. So that means there's a lot more places where people can go and hack. The other thing that happens with that transition, which is not often talked about, is for the past 30 years, and if you read anything about cybersecurity, and if you typically look at the news, chances are when you see a big news item having to do with cybersecurity, someone went and hacked a database or hacked a bank or hacked some place. They stole information or they stole money. That's what typically happens. So the final result is someone has lost their personal data. Someone has lost millions of dollars. But the thing that's happening in the future, and when machines are going to get hacked, when your pacemaker gets hacked, when your insulin pumps get hacked, or your grid gets hacked, or your power treatment systems get hacked, it's a different game. It's no longer money. It's no longer about the information. It potentially has life and death issues. So you go from this security to one of safety concerns. And from a policy point of view, as we've seen many of our things and many systems in our past, like cars, eventually you come up and you put laws or you put policies to ensuring people will have their seat belts. They're going to have cars with airbags. You're going to want to put safety measures in place in those systems. And usually with the speed at which the evolution of our systems happen, governments have a chance to keep up with the policy-making process to maintain fairly stable, livable environments. With the advances and the speed at which operational technology and smart things are now happening, and we're talking next 5 years, we're probably going to go in the range of 40 billion devices. That's a pretty fast speed at which it's exponential now. We're getting in the game that in the next 5 years, things will be available to those that want to hack our systems and do quite significant damages. So from a policy-making point of view, you have to start accelerating your thinking process, almost try and keep up as fast as you can with how do you ensure security and safety for the community. So I think from a policy point of view, what is happening and the trends that we're seeing and the positive things about making things smart, there's also the the negative aspect of it. So anyways, I think it's something to keep in mind in the going forward for sure.
Okay, so good answers. I want to just go into specific use cases. So I'm going to try to get very tangible too on where the opportunities and threats lie. So to quantum sensing, I'll just give you a few examples of where there's uses. One is gravitational wave observation. So they might not relate directly to what you're doing, but it's important to understand these applications. So you might know that in recent years, there's been amazing work on detecting black hole collisions, these kinds of things. And what we can detect in space, these gravitational phenomena, so basically collision of two bodies can ripple space-time and have an effect on Earth. We're facing quantum limits in how well we can measure those. Quantum limits sometimes are called shot noise in electrical engineering, the Heisenberg uncertainty principle, wave-particle duality. They all limit how precisely we can measure something. And so there is in the roadmap for LIGO, LISA, these different entities that are improving gravitational wave detection, that they need to use something called squeeze light to be able to surpass existing limits. So there's a real tangible effort to develop that capability. Another one, we heard about clocks And so clocks, I think clocks are as good as up to 1 second accuracy in the age of the universe. Sounds really good, but it's still not good enough. So there's a lot of effort going on to improving clock networks, and this could have implications to GPS, that kind of thing. I'm a little bit skeptical of it, but that's what it says in the literature. And then also imaging at single photon levels. I always think about, like in Hollywood movies, you see like, was it Maverick? Whatever that movie that just got I forget the name of it, the one with Maverick, Tom Cruise. Anyway, they're flying an airplane and then they say, oh, somebody locked out to us, and they dodge missiles. But if you could somehow image and detect aircraft at such a low light level they don't know they're locked onto, it would change the narrative in Hollywood movies at least. So that's important. In the secure communication, which Bruno's talking about, it's the one thing to remember is a forward security argument. And so when we send communication back and forth right now, an adversary can record it and decode it if and when a quantum computer is at scale. We're not worried about it today. We're pretty confident that quantum computers won't be able to do it. But for national security issues, we have to look forward 30 years. So if somebody records the communication today and cracks it in 29 years, it violates those conditions. So right now, quantum communication is relevant. And the Department of Commerce in the United States, through NIST, the National Institute of Standards and Technology, is on the verge of approving post-quantum crypto standards. And so it looks like in the next year, we're going to reach a point where some of the secure networks are going to be required to work with post-quantum crypto. Post-quantum cryptography is not quantum. It's using existing methods, develops algorithms, decoding and so on, but it's trusted to be impervious to quantum computer attacks. So the post-quantum crypto will be on board next year, and certainly in the US and for Canada as a Five Eyes country, it's going to be important to comply. So we can't ignore it. It's going to happen. And then finally, in quantum computing, right now, we understand from Raphael, like it's a time, there's a significant time to develop quantum computers that reach scale, but we are seeing big companies and small startups generate value even without quantum computers at scale. How can that be? How can companies make money off it? And the answer is partly it's what I call quantum adjacent. So it turns out that thinking about quantum computing unlocks some things in your mind so you can think more creatively about non-quantum computing. So the idea of studying quantum computing is allowing people to get creative and solve problems in different ways. What's absolutely vital is to deconstruct problems. And so it's something I think a lot about myself is, I talk to a company and I say, okay, what's your computational bottleneck? And it can relate to sustainable development goals. I've talked to hospitals, many others, and figuring out where exactly is the computational block that's hindering progress in various settings is actually very difficult. And so one of the things that we do in quantum computing today is we talk to a company, we say, what is your computational bottleneck? And then it could take months to figure out exactly what that is. And then we do it. We say, well, let's try it a different way so it's amenable to quantum computing in the future. And then we'll throw everything we have at it today, even if it's not quantum computing, to solve it now. So we're so ingrained in a historical way of thinking of computer science. Nothing wrong with that. It builds up from church and Turing hypotheses and elevates up. And it's so ingrained in all the application software we have that going back and saying, maybe there's a different logic at the foundation. Let's deconstruct it and put it in that way. That's what's creating value, is rethinking computational problems. So we can do that today, getting ready for quantum computers tomorrow, and we can actually solve some problems today. Thanks.
Maybe I'm going to add the first bit of controversy here. So I completely agree with all the applications that were mentioned. And it's interesting because the quantum computer that we're building is based on squeezed light, very similar to what's used in the LIGO experiments. We use photon number counting detectors, which were also mentioned as a potential sensing technology. It could be really well adapted to quantum communication purposes. And in fact, I believe we still do have a quantum key distribution system that we built in-house available for researchers through our cloud. But none of these are the areas that we're actually pursuing. We have IP in those areas, but we don't focus on them. And the main reason is that the impact that these technologies have is going to be incremental. Quantum sensing has existed for quite some time. QKD systems have been around for a decade, have, had a problem in terms of actual adoption. Quantum computing is a little bit different. And I'm not talking about the near-term quantum computers that we have today, but that promised million-qubit quantum computer really does represent a transformational change to certain problem areas. And probably the one that is most applicable in natural resources is the ability to simulate quantum systems with higher efficiency. So whether it be for greater accuracy or with the speed up. Still a lot of work to do, but a lot of the work that we focus on is trying to understand how to build algorithms for specific problems that our partner companies have. One we recently announced publicly was with Volkswagen, and was about building fault-tolerant quantum computing algorithms. So again, that million-qubit quantum computer to start tackling the problems around building next-generation batteries. This is still very experimental, or I should say theoretical work. This is not running on any device today. But if we could deliver on that promise, that is truly transformational. That is doing something we fundamentally can't do today, no matter what scale of a computer we have. So often when we approach partners, whether they be academic, government, corporate, we try to get them to think about what risk does quantum computing pose for you, not just in a negative sense of breaking cryptography, but what if you're a chemical company and all of a sudden your competitors could do all of their design in silico? What if you could find a better catalyst for carbon sequestration? What if you could model transition metal catalysts, whether it be for green hydrogen or other purposes, to a much higher degree, so you don't have to do any wet lab work in order to actually generate them? These have truly transformational impacts. And I think in that respect, not quantum computing today, but the promise, the reason why there is all this hype around quantum computing, it is a little bit different than many of the other quantum applications that we speak about around sensing and communication. I should point out that in both of those, there is really exciting possibilities that are very forward-looking that will be transformative as well. But often when we speak about quantum communication, quantum sensing, we do also include the things that we're doing today that are these incremental pieces.
Thank you so much. Can you hear me? Okay, so thank you so much. And I think part of the challenge for us in government is how do you convince government to invest in a potential idea that may or may not happen 30 years from now. And it's quite challenging when we don't have the very tangible use cases. And those are evolving bit by bit. But one of the challenges is a potential threat is hard to fund until there's an immediate threat. And then you're too late. We've got a few more kind of pre-prepared questions, but I did want to turn it over to the audience in case you had questions. And if not, then we could infuse a couple more questions. So I see a question all the way to the back. I don't know if we do have a mic somewhere there, or if we could share one of the ones we do, or you could just scream it out. Okay. So the question is around materials development. So the materials component of quantum, right. So this is the more solid part of it. I'll turn it over to you, Barry, in a second. Any other questions? So we have at least a couple to percolate on. Okay. Yes, go ahead.
Perspective, where does Canada stand in all of this? Are we well positioned to win this race? And if not, what will it take us to get there?
Great question. So are we well positioned in this whole race for quantum? And if not, what will it take for Canada to be at the forefront? Let's take maybe one more question. Okay, folks, a little shy, so I'll turn it over to you, Barry, and then I open it up to the panel to answer to either one of the questions.
Okay, the quantum materials question, the materials question is an excellent one. So I quickly wanted to jump in and give my own response. First of all, I wanted to emphasize that within Canada, the list, sensing, communication, computing. Materials is also on the list. When I didn't say materials there, my own thinking is that materials are absolutely vital for the success, but I look at it as an underpinning technology. To me, materials must be there. When we talk about materials, there are different ways to think about it. There's regular materials, there's smart materials, topological materials, nanomaterials, and so on. So there's different categories of materials that we want to develop. All of them can be relevant. So there's, on one level, if we think of superconducting quantum computing, IBM and Google and so on, one of the performance limitations is how good the superconductors are. And in Canada, for various reasons, there's been an amazing effort. Superconducting was a big topic in the 80s, and for various reasons, it was sustained in Canada. So we punch well above our weight in theories and experiments related to superconductivity. And those kinds of developments have been really important for pushing forward that technology. And then we can see within Canada real strengths in the area. A startup in Sherbrooke, for example, that is, to me, it's very impressive. And so making the materials right is important. It addresses those limitations. Also, the other ones like topological, so on, there's radically different ideas in how to develop quantum computers. Microsoft has invested into topological quantum computing. I won't go into what it is, but there's real material challenges in that. So we always have to be aware of material development, both regular material up to quantum, topological, nano, et cetera. These are all really important in the story.
Maybe just one thing to add from our perspective is the scientific development of these materials is great, but building up the manufacturing capacity in Canada would actually be phenomenal. One of the problems that we have is our major cost realistically is foundry runs. We work with various material stacks for photonic integrated circuits, but we don't leverage any of the fabrication facilities within Canada because unfortunately they're doing very important work, but very traditional work that has been happening for quite some time and aren't pushing the limits of the more novel materials and applications that people are looking at. So I would encourage, from a policy point of view, to again understand that commercialization problem, not just the great science that always has a tendency of happening in Canada, but then understanding how do we actually move past that to build the commercial entities that can exploit that scientific research.
And for the second question, any comments or reflections around where is Canada? Are we ahead? How can we push forward our position in this quantum race?
I'll give one point of view here. Canada seems to have, again, in many fields, always come out with a very strong starting position. We definitely, from a technology point of view in the quantum, punch way above our weight class. And it's the same in the security side of things as well. Very, very strong. But it takes money to get these things going. And if you look at, I think it was McKinsey that came out with an assessment of the money having been spent in recent years in the world, of the $30 billion out there that's been announced and publicly announced, half of it, I think, was done in China, followed by many other countries. And Canada has 0.6 billion, or 0.6 is their value. It ultimately comes down to spending money to keep the brain, to keep the talent, to build the technology stack, and so on. We definitely have super strong technology and expertise and capability. But to keep it and maintain the leadership, you need resource, cash. That's what it comes down to. So I think that's long-term. It's the answer you may want to look into, where follow the money.
Amy, did you want to go, and then Barry, over to you?
I'm going to hop on the talent bandwagon on that one. I agree fully on the resource in there. We don't have enough quantum talent to sustain where we are, even where we are now, let alone where we need to grow in the future for the Canadian ecosystem to be pulled into the different end use sectors. So one policy option consideration there is what are ways we can better import quantum talent. I've heard from a lot of different projects are just finishing their first year right now, and a lot of them are complaining about extreme delays on their projects due to trying to get talent to come to Canada, to get those postdocs and students to get their visas in to get here. So that is definitely an option there. That as well as what Shahini was mentioning, that our growth of talent here in Canada there, and not just a bunch of physics nerds, but what about the quantum engineers of the future, or even forget about that, expand even further to be the true interdisciplinary people who are not just the quantum experts, but who are quantum aware, but are very good at these other areas that are needed to actually make this relevant and usable in these end use sectors. So I think a lot in these areas will help going. So, but overall, just increase coherence along the way, and hopefully, as was mentioned, I think in a few of our earlier panels today, hopefully on the international scene, a little bit more. Be able to import and share what we're good at, and be able to collaborate and be able to bring some of their expertise to Canada to build some really impactful projects.
Okay, so where Canada stands, as we heard, it punches above its weight. This is all demonstrable by just looking at seminal papers and how many have Canadian addresses. In the National Quantum Strategy document, the earlier one, it's written out. So there's actually a document that lays out how Canada's played a key role. I wanted to address the point of how Canada can be great, and it's probably a little bit different than what we heard. I don't think that Canada is able to rise, like we're doing well in our weight class, as you said, but whether we're going to rise to be the world leader, world domination in quantum, I don't think it's going to happen. For 20 years, I've served on European Commission panels, which has been very interesting, and various things in Europe. And so in Europe, it ties together a lot of countries, right? So you've got 300 million people south of the border. We've got hundreds of millions in Europe. In Europe, they're finding ways to work together. It's all collaborative. And Europe is doing really well by working together. And many of those European countries individually have a greater population than Canada. The problem we have here, we have the brain drain. We have to find ways to retain talent. But my view is, we really have to take a lesson from other places, and we need to find a way to play together well. We depend a lot in the U.S. at the moment, but we're very small compared to the U.S. We have to find a way to collaborate with various parties, find ways to exchange. And this is a big, big barrier in Canada, is we're not so good at working well with others. We have a lot of Canadians that move out, and then the interactions are negligible between them. And so, I think we have to take a lesson from what Europe is doing and find a way to develop partners and work together, and not try to throw all the resources at making Canada the best. We are the best at certain things, but we need to work with others.
Maybe I could just add how proof points on both of those. 60% of our workforce actually came on work permits or visas. Most of them have become residents or citizens of Canada at this point. But without being able to import talent efficiently, quickly, a company like Xanadu wouldn't be able to exist. And similarly to Barry's point, one of the really big dangers that we're looking at is the export control legislation that's probably right around the corner, based on what we've seen from the US, from other international partners. And that could really limit our ability to develop, as a whole industry, quantum technologies. So like I mentioned, our manufacturing partners are international, but we have research collaborations across the globe. And it's really important to keep those open in order to be able to sustain the development that we're doing. One thing I'd like to point out, though, is that compared to other jurisdictions, even if you pick one country from the EU, Germany is one example where they're investing very heavily. But not only are they investing more, they're also investing much more strategically. So they're picking clear areas, clear winners that they know they want to support, instead of trying to appease everybody and spread the funding out across as much as possible. And unfortunately, the truth in quantum is that all these projects are very capital intensive. And something like the quantum strategy, though it seems like a lot of funding, in one piece gets broken apart into so many small projects that it's hard for that to actually make a true impact on the commercial scale.
I just want to make a couple of points related to the quantum race, but it also goes back to what you were saying about, your controversial point that the quantum computing is transformational, but perhaps not QKD or communication. But really, if you think about it, tomorrow, if we could really build a network that is, encrypted using fully quantum techniques, and it really works, meaning, to the right level of, error-free operations, then that's transformational in the sense that no matter how powerful of a quantum computer or any other computer you build, you're not going to break it because you'd have to break the laws of physics to break encryption. So in that sense, transformational. I know yeah, but let me finish. Now it's getting interesting, right? So let me finish. So my point is, okay, let's then take that and think about it tomorrow or whenever, maybe not tomorrow, but in a few years, if all of Canadian banks, let's say, get together and develop this, super secure quantum-based encryption, and all of our data, all of our financial data is completely secure, we can trust it fully within Canada. We don't win the quantum race because, of course, our banks talk to banks outside of Canada. In fact, all of our systems are constantly talking to everybody else. So I don't think we can talk about winners of a quantum race because we will either all win or all lose. I think that's perhaps a better way to think about it, which goes back to Barry's point of playing well with others.
We can challenge, but I'll always say that for quantum QKD systems, for quantum security, I'm never worried about the quantum side, even though there's often attacks that people have shown for certain things. It's so hard to build a secure system. Sure. Bruno will tell you all the different ways that you can attack QKD systems, from side channel attacks. It doesn't matter what you pick. Building a secure network is almost impossible.
But Junwei Pan would argue that you can.
They also like quantum annealing. So.
I think Bruno's rubbing off on Shohini. Bruno, over to you, and then we have a question from the audience.
I'll do this fast. One very interesting thing, and I mentioned it at the beginning, when we're going from the world of IT that we know, where we are concerned about information, securing the information during its transfer and all, it's really important. Confidentiality is what we're dealing with here. When you're trying to think of smart cities, smart cars, smart manufacturing, it's identifying those devices. It's all about availability of these devices. You don't care about confidentiality in those worlds. So the world of tomorrow really doesn't really deal of, it's not super important to have confidentiality. It's all about identification of those devices, the integrity of those devices. QKD is not going to solve that. So even though QKD could solve quantum, with quantum technology, we could do lots of really cool stuff about confidentiality transfers. When we get into the IoT world and the OT world, it will be a different game. It's a changing world. And what we're going to have to do as security experts is to start applying different techniques. It's not about QKD, it's about post-quantum cryptography in that sense. So I would suggest that, yes, QKD can help, but it will not help solving all the world's problems in the future. It'll be a slice. And I can tell you there will be lots of challenges going forward. So that's my point.
Thank you. So we have a question from the audience. So please.
Done some analysis on the quantum technology part. So it's the research aspect. Canada stands at number 7 in terms of its publication output globally. China, as you mentioned, is at the top, right? Because they're getting the funding. But in terms of quality of what's being published from Canada is definitely much higher. I think the only other countries which compete in terms of quality is the European countries, where you have Germany, Switzerland, and UK doing well in terms of quality. So I think there are different aspects which would need to be considered when it's the funding, but from the research aspect, there's good amount of research happening from Canada, good quality research that's happening. It's just about continuing the momentum over here.
Mm-hmm. Thanks for that. And if there aren't any other questions, I think, okay, there are a number, which is great. So over to you, gentlemen, on this side, and then there's a question over at the corner.
Great, thank you. My name is Peter Stephenson. I'm the director of the policy team at MyTax. So MyTax thinks a lot about innovation policies. That's our mandate, to support innovation development in Canada. And when we're thinking about quantum, I guess, we're lay people, so we're not experts. But the two big kind of features that stand out for us is that, yes, Canada has its advantages in research and talent. I think that's pretty clear, and it's been demonstrated a lot of places. But in terms of the overall funding environment, our amounts are vanishingly small relative to something like China or the U.S. or something like that. We've heard stories that there are individual VC deals in the U.S. that are bigger than the entire value of the Canadian quantum strategy. So looking at that, when I start thinking about Canadian innovation policy, I start thinking more about things like some things that have been brought up here, like quantum adoption. Maybe we're not going to be the leaders in developing the core quantum technologies, but maybe we become the leaders in applying those technologies in natural resources, in chemistry, in material sciences, stuff like that. Alternatively, maybe we become the leaders in manufacturing. Maybe we develop the ingredients. We cover some bit of the supply chain that leads into the quantum industry. So it's those quantum adjacent areas that I'm very interested in. I'd love to hear opinions from the panel about whether you see big opportunities for Canadian innovators in those quantum adjacent areas.
There's a question over at the corner, so I'll let you go ahead.
Okay, there was a report called I think What We Heard, and recommendation number 11 said, and I want to ask the panel if they want to speak about the urgency here. Recommendation 11 said that the government of Canada should strive to complete and release a national quantum strategy by March 1st, 2023. And this is the fun part. If that timeline is not met, the Minister of Innovation, Science, and Economic Development should appear before the House of Commons for 2 hours to provide an update.
I think I'll piggyback a question that I think will link to some of the connections around MyTax, around government, which is how can we more effectively link public, private, and academia in scaling quantum technologies? Because I think it touches a little bit on what we're doing. And then we're standing between you and lunch, so we'll try and get through what we can. So over to you, Rafael.
I just briefly want to respond to Peter's question. So I feel like I need to wear sometimes my Avro Aero t-shirt to these types of talks. And it's because I feel a very similar story has happened in Canada repeatedly, which is we do the fundamental research for phenomenal, great technologies, and we export all of that intellectual property overseas to be commercialized. We've seen it, Avro Aero is a bit of a joke, but I think it began there. We've seen it with photonics. We've seen it with mobile communications. We've seen it even more recently with AI. The fact that core teams, academic teams that really built the tech giants of today could have been Canadian. And I do think it's that maybe smaller thinking of, well, we can't compete on this international scale, that attitude needs to be changed a little bit within the policy side. Thinking about not, what are the multinational tech giants that are operating in quantum telling the government, but think more about how can we build this as a homegrown industry that will then spin off all the adjacent things. If we build quantum tech nationally in Canada, have that core competency, the application startups will be here. The manufacturing startups will be here. All those other core technologies will be here, and we're already seeing it. There's great companies in Alberta, NanoTools being one, 0 Point Cryogenics being another one, that really are now being started up because the demand is local within Canada and we can actually support those partners. I'm not sure how we do it, given the dollar amounts that are available, but I think it would be a shame if we just said we can't.
Maybe we work our way this way. So Barry, if you wanted to jump in on any of the questions asked.
The mic's gone.
Bruno stole it.
Oh. Sorry, the question is?
there's a number on the table. So there's building capacity. There's us, the timelines around the national quantum strategy, and then there's the link between public, private, academia to really advance quantum within the Canadian context. So
Maybe
whichever one of those.
I'll take the last one, and then I'll pass it on. So building that public-private dialogue. The way I think about it right now is, a lot of the quantum strategy has been driven by creators of knowledge. So I think of it like a push and pull. So for me as a quantum scientist, I love the field. I wake up in the morning thinking about it. I go to sleep at night thinking about it. And I want to proselytize. I want to convince everybody it's good. It's good to have people like me in the system who push the idea, but we need the pull. And the pull is starting to develop where, like in Calgary, we had a summit recently. We had various companies show up, and we're trying to figure out what exactly the problems are out there, and then match up these things. And so this is where we need to go next, is to figure out what the problems are, what we know, to have these kinds of dialogues, to look for the little wins along the way that build confidence towards the big ones. And then MyTax, I think, fits in beautifully. MyTax is an organization that really enables that bridge through internships, through project funding, and all that kind of stuff. MyTax has incentivized a lot of activity to go away from the purely academic realm. Certainly for me, it's happened where, instead of me thinking about, one of the things I'm thinking about these days is whether if I could make time travel inside a quantum computer, would it help? And of course, nobody's really going to do that, but that's the kind of thing I like to think about. But with MyTax around, then I start thinking about, okay, there's an oil company or there's a health issue like, identification of disease on the scale of minutes instead of taking days to get a result. And then I start thinking about quantum technology in that direction, having resources available, and my students want to do that kind of thing. It's pulling me into the problem area. So I think that kind of thing and what MyTax is thinking about are absolutely vital for pulling academics into the real world and the applications.
From a point of view of where Canada and adjacent technologies and the types of investments, one place where Canada has in the mid-90s been quite advanced, again, very early in the process, when the internet became a thing that we could use to deploy, building corporations and starting to make money on top of the internet. There were things that were critical to securing that foundation. Technologies like PKI that got developed here in Ottawa by companies like Entrust, hardware security module that were developed here in this town. And Canadian technology became the core foundation of securing the internet for the first wave, I'll call it the digital economy. Where we're going next, this talent still exists. This talent still lives in Canada and has basically bred lots of companies. And I think one area where I've been agitating the flag here, as we're advancing in the quantum world of tomorrow, we also have to maintain the secure world that we have today, and we have to maintain that. I think from that perspective, considering the adjacent portion of quantum that's ensuring, securing what we've already got, might be a place to consider the investments in guarding the world that we've built so far. So I would suggest that's definitely a place where Canada still to this day punches really high on the world class of companies. You have world-class technologies being deployed here, developed here, sold across the globe to ensure that internet security that we live in today. So that would be one place where I would consider, thoughts.
So I think some of these questions are related. So, for example, if we're going to talk about how to connect academia, industry, government, that's actually something that is going to depend on what this national quantum strategy is, because based on what that rollout is, that will drive how we build these kinds of connections and collaborations. For example, currently the pieces of the national quantum strategy that are announced are basically funds for existing programs such as alliance grants, which is, an academia industry kind of partnership system. So that's what, since that's announced, that's what people are working on to develop. So in that sense, I think the strategy really will be, in the end, what will answer the question of how we're going to be connecting this. But as they develop it, I hope that we go beyond the existing structures, because quantum is new enough and it is interdisciplinary enough that we can really use that as a way to create new types of connections and focus, I think, a lot more on, I think of it as almost like a quantum app store development model. Because before the app store existed, I mean, who could have ever predicted the number of different apps we would have, right? So I feel like that's the kind of model we need, where we have to go in without saying, okay, this is what we're going to build, because we already know. We don't know really, and it's impossible really to predict this kind of technology. So I hope we can think more about models like that to be able to create this sort of real revolutionary approach to quantum technology.
I can't speak to what's in the National Quantum Strategy or when it's going to come out there, but a few of my colleagues were in the UK last week touring around to see what they've been doing. And the UK has had a National Quantum Strategy for 10 years already, and that has allowed them to really focus on certain areas there with that main goal of trying to push towards commercialization. And that has been really good. But one of the observations my peers were making there was like, to the questions we've all had, I think a few of the others might have been there too, is quantum technology is still hard. There's still a long ways to go there. Like having a coherent national strategy for them, I think, has helped, but they haven't solved everything yet. Here's an example of it. Now I'm going to take my sensing hat off, which I've been having all day here, and put my comms hat on. Say for Canada. Canada is the second largest landmass in the world, the country. For quantum comms, that is something that has to be led more at a larger level to have the infrastructure to remotely make QKD to be interesting, or the next generation beyond that, more of the quantum internet of sharing, entanglement, connecting quantum computers, that type of thing. And that type of, to make that a reality, that has to be kind of a push from above on the infrastructure side there, because if we're going to have dedicated quantum or fibers, that's not something we can hope that the industry is just going to pull. That has to be a lead thing. So I think there's a delicate balance there and what you can get out of a national strategy. And I do hope, I am looking forward to, like, as with everyone else, to see when it does come out there. But I think there is a lot of work to be done and a lot of leadership to be had by a lot of players.
Thank you so much. And I'm standing between you and lunch, so I'll keep this very, very brief. Just to the MITAX question, the lead policy advisor within my team who's been helping us advance this work was a former MITAX fellow with a PhD in quantum and a policy background. So it's like those unicorn people that you come across, and I'm like, please don't leave us, not just yet. So there's a lot of great things that come from these public-private partnerships. For the NQS, it is very imminent, is what I can say. If we bump into Simon Kennedy, who's the DM of ISET, Deputy Minister of Innovation Canada, he could let us know how close it is, but it is quite imminent. And I think having the strategy has allowed us to have conversations with senior management in ways that we wouldn't have had that strategy not existed. And so it is allowing us to have those policy conversations with senior management on something that's very technical, because it is creating that environment. And I hope that within the Canadian landscape, having leadership from the federal government will help us advance not just the conversation, but also the investments. So I want to take some time to say a huge thank you to our panel. This was an extremely robust conversation. I'm always surprised at how well folks engage with something as abstract as quantum. If I had to go back to school, I would become a quantum physicist, although my physics teacher will probably say, maybe you're not cut out for it. So huge thanks to you all. And I do hope that, again, this conversation continues. And I also thank you for your participation and your attention. So go forth and enjoy your lunch. Thank you.